All right. So the first one on 453 was 47. It says photographers often put polarizing filters in front of their cameras, and that will serve to make clouds more visible, right, and then darken like the rest of the sky. So explain that based on what we know about polarized light. So Sophie, what'd you say for that?
I said that by using a filter, the photographer can reduce the amount of polarized light from the sky reaching the filter, but that means that the light from the clouds must not be polarized if it doesn't get affected by the filter.
Right, so when we played with these polarizing filters last class, we saw that a single filter didn't do too much to most of the sources of light. It darkens it up a little bit, but we did have some surfaces where a single polarizing filter could do a lot. So some of the surfaces we saw were the glare off of the countertops and the desktops, right? So we saw that the glare was kind of polarized. What else did we see that was emitting polarized light? The projector was definitely emitting polarized light, right? We had the one, yeah, I guess we can see it when I stick it in front of there. So we had one direction of polarization for the red and the blue light that the projector emits, and then a different direction of polarization for the green light. And then I think the phone we saw, the display screen was polarized. So the single polarizing filter will remove some directions of polarization. Apparently, right, the clouds are emitting non-polarized light if the clouds stay nice and bright when the photographer places the filter over top. But then the rest of the sky is polarizing the light a little bit. So at least that would be the most consistent explanation of what we know about polarized light. Other issues with 47? All right, 48 had to deal with our colors. So we have an apple is red because it reflects red light and absorbs blue and green light. The first question was, why does red cellophane look red in reflected light? So I actually put our filters away, but if we pretend that this is red cellophane and we look at it, right, it kind of looks red. So Henry, why does it look red? Why does the light that it reflects look red?
Why does the light that it reflects?
Yeah, that's a somewhat different question than what it's asking, but I think it's a better question.
Oh,
so why does the cellophane look red when it's like illuminated by the overhead lights or whatever?
I said because it's letting blue and green light pass through it, but it's blocking the reflecting red light.
That's actually the exact opposite of what it does. So the red filter, right, if we look through it, we see red because it absorbs the blue and the green. Right? The red light, the blue and green light don't get through it at all. Right? Only red light can get through it. So it's absorbing blue light and green light. That's going to just serve to heat up the filter. And normally the filter will let red light through, but if we look at it, this is stupid to use something that's not a red filter. If we're having trouble, let me grab one. What color is this? Pink. That's magenta, pink. Alright, I think I have something. Oh yeah, here we go. Alright, what color is this one? Red. Alright, so we have what kind of light hitting it? White, right? So all colors, all frequencies from the overhead lights. And this is a filter, so red light does pass through pretty easy, but some of the red light will reflect. Alright, so if I kind of hold it like this, some red light, instead of passing through onto the whiteboard, should reflect towards you. But now the blue light and the green light is totally absorbed by the pigment molecules. So it looks, the light it reflects looks red because the blue and the green gets absorbed. Some of the red gets reflected, most of it actually goes through. Follow-up issues about this looking red. Alright, the next part was why does cellophane make a white light bulb look red when you hold the cellophane between your eye and the light bulb? I mean, we kind of already talked about that. It's absorbing the blue and the green light that hits it, but it's letting most of the red light pass through. And then we already addressed C, what happens to the blue and the green light. They get absorbed by the molecules in that pigment. Follow-up issues with 48. All right, 52. So 52 was a Doppler effect problem. And it was the first time we've considered a Doppler effect problem for light. So I've already done my first few steps. I already have my sketch, which shows the red light, emitting red light. We have, I don't know, who's that? That's Tim, fine. We have Tim driving towards the light. And Tim I guess maybe that's a good choice. A little bit of a wise guy, right? So if he got pulled over, I don't think it's a total stretch to envision Tim arguing science with the police officer. Just never a good idea. Never a good idea. But Tim's going to say, no, I saw green. It was green. I was going fast enough that it was green. So the police officer, right, wants to find out how fast Tim would have to be going in order for this red light to be shifted towards a short enough wavelength, a high enough frequency that Tim would see green instead of red. All right, so I've already identified variables. The wavelength of the source light is 645 nanometers, right? 645 times 10 to the negative 9th meters. If Tim is seeing green, then he's detecting 545 nanometers, 545 times 10 to the negative 9th meters. The speed of the light, regardless of if it's red, green, whatever, is 3.00 times 10 to the 8th meters per second. The speed of the source, the traffic light, is 0. And then we need to find Tim's speed, or Tim's velocity, right? And I only know one equation for Doppler effect. Well, at least there's only one equation for Doppler effect on our equation sheet, and it's this one. All right, so let me do a pause and ask if there are questions about my step 1, step 2, step 3, or step 4. Bert. A little tiny bit louder.
What's the point of converting from nanometers to speed?
What's the point? We should be doing things in SI units. You're right if we put it into the equation with nanometers, as long as they're both, well, nanometers doesn't actually show up in the equation. But if they are in the same unit, any Doppler effect equation we use should work out all right, so long as we are putting in both frequencies. But we should be working with things in proper SI units. Trudy.
In the textbook, there's like a different equation where
Yep. That's fine, but you're not going to have access to it for your test on Monday, so I'm not going to use it. And, I mean, I don't think you guys should be memorizing like alternate versions of the equations we use. There's no need to. We can arrive at those other equations from the ones that are on our equation sheet. Hi.
I just follow up. So if I did that on the test, I get converted to meters, but I have to convert to meters in order to get the full credit. Or
So I'll answer your question, but that's not a great question about this one, because wavelength does not show up in there, right? So I'm not putting these values into that equation. But if you did that on the test, I would probably be okay with it as long as you were consistent. But you're only going to get me to commit to probably. All right. So these are not frequencies. I can't put them in that equation. Fine. Maybe you, like Shruti, you found some other equation that had wavelength in it, but I'm not going to do it that way. So I want to turn these into frequencies, right? And I can do that because I know that wave speed equals frequency times wavelength, right? So if I want the frequency, I can take the speed and divide it by the wavelength. And that's exactly what I did to turn both of these into frequencies. So the frequency of the source light would be the speed of the waves divided by the wavelength of the source light. 645 times 10 to the negative 9th meters. And that ended up being, what did I get for that? 4.6512 times 10 to the 14th hertz. So we're getting, oh geez, what is that? Almost a million billion compressions and crest and troughs each second, right? Extremely high frequency. And then, so that's the frequency of the light that the traffic light emits. The frequency, and we still need to find the frequency, bless you, of the light that Tim's going to see. So again, that's going to be the speed divided by the wavelength. All right, and that's the 545 nanometers, or 545 times 10 to the negative 9th. And that will be 5.5046 times 10 to the 14th hertz. And I think the drawback of doing what Bergen wants to do is when you do this, well, then what is the unit? It's not hertz. You know, is it whatever the prefix for 10 gigahertz? Probably. Maybe gigahertz. I'd rather not have to think about that. I'd rather just get rid of the nanometers from the start. All right, questions from anybody on converting the wavelength of the source waves or the detected waves into their frequencies? If you didn't do that, well, if you guys used a different equation, I'm curious why we're going to end up getting different answers. All right, so what I chose to do next was solve this expression for my unknown, for my velocity of the detector. So I'm just going to do a little algebra to get that isolated, and then we'll put our values in. Please watch closely, because I'm not thrilled that I have a different answer than Mr. Zitzowitz. So please, watch carefully, and if you see something that looks like bad algebra, let me know. So I want to solve for this. The first thing I'm going to do is divide the FS. Divide the FS on both sides. So I'll get the frequency that Tim sees divided by the frequency the light emits equals V minus VD over V minus VS. Any problems with my algebra there in dividing both sides by the FS? I'm getting one person saying no, but it's the only person that had the same answer as me. So can I get somebody else saying, yeah, that's okay? Yeah, that's okay. You did? You had negative 5.5 times 10 to the 7th?
Oh,
no, you didn't. I was checking. Well, I post Mr. Zitzowitz's answers. Usually they're the same as my answers. This time no. All right, so we're okay with that step. Next, I want to multiply both sides by my denominator over here. So I'll have FD over FS times V minus VS equals V minus VD. Anybody want to yell at me about my algebra there? I'm serious. I think maybe I have a problem with my algebra. That's why I keep asking. Okay. I want to find VD. What I chose to, I don't want to find negative VD. I want to find positive. So I'm going to add that to both sides next. So VD plus this whole term. Okay, anybody want to yell at me about my algebra there? No. All right. And then I need to subtract this from both sides in order to isolate for the speed that Tim is driving at. So VD will equal the speed of the light minus the ratio of the frequencies times the speed of the light minus the speed of the source. Anybody want to yell at me about my algebra in that last step? All right, I need to move on to the other board, but now I'm going to go ahead and fill my, my values in. So again, we're trying to find the speed that the detector Tim is driving at. The regular V is just the speed that the light is traveling at. So 3 times 10 to the 8th meters per second. Then I'm subtracting the ratio of the two frequencies. So FD is the 5.5046 times 10 to the 14th. And then the frequency of the source is the 4.6512 times 10 to the 14th. And then I still have the V minus Vx. So 3.00 times 10 to the 8th minus 0. Okay? Now anybody want to yell at me about filling in the values? Yeah, Alex.
Wait. No, I don't. Never mind.
Alright. Alright, so what do I want to do next? Next, I guess I'm just gonna get rid of the 0. Or I'm just gonna erase it. Save myself one line of writing. Does anybody want to yell at me about getting rid of the minus 0? Okay. I'm going to find this value next, right? So what that ratio is. Alright, so I got, what I get? 1.1835. And then I do need to multiply that by the speed of light. Alright, anybody want to yell at me about the next step? No? Alright. And then I'll go ahead and multiply these together. Alright, and so what did I get? I got 3.5505 times 10 to the 8th. Anybody would yell at me about that? And then my final step is just subtracting those two things. So I get negative 0.55 times 10 to the 8th. Or if you like proper scientific notation, negative 5.5 times 10 to the 7th meters per second. Anybody want to yell at me about that step? Now, I like that it's negative. I like that it's negative because we used a positive value for the speed of the light, and Tim is going in the opposite direction, so it actually better work out to be negative. And yeah, that's definitely a different answer by about 20% than what Mr. Zipsowitz had, and he had positive, not negative. So any other follow-up issues about my solution to finding the speed that Tim had to be driving at to see this red light as green? What's that?
Are you right?
Nope. How many of us are here? 18 of us? 17 of us? We went step by step. We found no problem with my algebra. Yeah. I mean, unless you can point out to me where the problem is, I am quite confident that this is right. I mean, it has to be negative, but Mr. Zipsowitz had a positive answer. I think I know what he did. I think he pretended these were frequencies. And that's the only way we get the answer that all of you got, was by pretending that these wavelengths were frequencies. I don't know how else we could get the answer he got. Victoria?
I usually like the other equation
Okay.
in the book, like for light, and I got the answer in the book, but like you actually put the wavelengths directly into the equation.
Okay.
So I mean, I don't know.
Yeah. I don't see anything that we potentially, and you got a positive answer or a negative answer?
Well, it says it's a negative answer. The two things are like moving towards each other.
Well, one of these things isn't moving.
Oh yeah, but like after I did like the initial algebra, I got a negative answer, but then I said like you had to make that negative since like one thing is moving.
Oh, that sounds confusing.
Yeah, I don't know.
That sounds confusing. That makes me like whatever other method Mr. Zipsowitz is using even less.
Like the answer I got was for the overall answer was what you had for the frequency of the source. Well, it was 4.651.
I think that's coincidental. I think
Oh,
that's coincidental. Yeah. I mean, that's the same answer I got when I pretended that these wavelengths were frequencies. Yeah.
Wait,
Yeah.
so like,
I just-
was that intentional by the writer of the book?
No.
Or was that an accident?
No, they make mistakes.
Oh.
I just checked my work and I got it.
One more
I
time.
just checked my work and I got it.
Oh, so, okay. All right. Yeah. So, all right. So, yeah, these Doppler effect problems aren't the easiest, especially when they give us wavelength instead of frequency. Yeah, for sure.